Alright folks, we had a lot of fun with graphing, didn't we? And now we get to move on to trig identities and all the things that we can do with trig identities, which is going to include your second favorite thing, which is proving things. Aren't you excited? Okay, so the first section that we're going to talk about deals with just our fundamental identities. Just be forewarned, you're going to be learning a lot of identities, okay? So numerous identities that you are going to be responsible for knowing by the end of the chapter. Okay, so what is a trig identity? Well, a trig identity is simply an equation that holds true for any value that you plug into it. Of course, with the exception of those values that would make it undefined. So, in fact, you already know 5 trig identities. The first 3 that you know are the reciprocal identities, that cosecant is equal to 1 over sine, secant is equal to 1 over cosine, and cotangent is equal to 1 over tangent. The other 2 identities that you already know are the ratio identities, which is that tangent is equal to sine over cosine, and cotangent is equal to cosine over sine. So the next 3 identities you may not be aware of, but now you will. All right, so they are the Pythagorean identities. So the first one is that sine squared plus cosine squared is equal to 1. And I will not let you leave my class without knowing that. Okay, so sine squared plus cosine squared is equal to 1. 1 plus cotangent squared is equal to cosecant squared. And lastly, 1 plus tangent squared is equal to secant squared. So we have, right now, we have these 8 identities to use. You're going to be learning a lot more later on, but for right now, these are the 8 identities that we're going to be focusing on. What are we going to do with them? Well, mainly we're going to be using these to simplify expressions, whether that's in the course of solving an equation, or maybe to put it into a proof, or we might be using these as well to evaluate certain trig functions at specific angle measures without a calculator. So think about how would you evaluate the sine of 15 degrees. Without a calculator, you would have to use one of these trig identities that you're going to be learning in the future. Okay, so let's jump into some examples. First of all, what I want to do is I want to prove one of these Pythagorean identities. And I'm going to, in the course of that, we're going to see why these are called the Pythagorean identities. So the first one is that we're going to do is that 1 plus tangent squared theta is equal to secant squared theta. Now, the way that we're going to be doing this proof, we've talked about this and discussed this in the past, is we're going to take both sides of the equation and treat them as separate expressions. And you're going to simplify both sides, or maybe sometimes it's just one side that you simplify, but we'll get there. But you can simplify both sides individually and eventually show that both sides can simplify down to the same thing. And because of that, this equal sign that we have here technically does not exist. So this isn't an equation that we're actually going to be looking at. We're going to be looking at the expression of 1 plus tangent squared and the expression of secant squared, and show how these two things could actually be equal to each other. And if you can prove that, if you can show that, then you can prove that this equation is true for all theta. So what we're going to be doing is we're going to be placing this bar wherever the equal sign is. I want to see a bar. And that is simply to keep you organized, but more importantly, to keep you from using properties of the equation that you would normally want to do, like multiply both sides by the same number, or divide through by something, or maybe like subtract 1 from both sides, so you want to move 1 over there. Those are all properties of an equation that you would use algebraically to solve it. We can't do that because it's not an equation. So what can we do? Well, based off of this right triangle, if this angle right here is theta, then we can actually substitute what tangent of theta is and what secant of theta is based off of the x, y, and r. So that means that tangent, or the left side, is going to be 1 plus y squared over x squared. because opposite over adjacent. And then secant, which is the reciprocal of cosine, would be r squared over x squared, or 1 over that, correct? So it's 1 over cosine. Okay, so then what we're going to do is we're going to simplify this expression, meaning that this 1 can be written as x squared over x squared, and then this is r squared over x squared. And now we're going to try to get this side equal to that side. It doesn't mean that we can multiply through by x squared, though, because there's no equal sign here, right? Okay, so the next thing is let's combine this and make this one fraction. And now what we see is we have x squared plus y squared in the numerator. But if we go back to this triangle that we have, it's a right triangle, and we know by the Pythagorean theorem that x squared plus y squared is equal to r squared. So I can replace this numerator with r squared, and I now have the exact same thing on both sides. And once you have achieved that, you've now proven that this equation is true, and you're done. Some people put a check mark here, put a smiley face, whatever you want. You just know that you're done when you get the left side and the right side equal to each other. Okay? So you can see why these are called Pythagorean identities, because you end up using the Pythagorean theorem and replacing x squared plus y squared with r squared at some point. Okay, so that was a type of proof. The other type of thing that you're going to have to do is simplify expressions. So if you had this expression cotangent theta over cosecant theta and you needed to simplify, without going to the x, y, and r, we can actually use our reciprocal identities and ratio identities to simplify this. So for example, cotangent is written as cosine over sine, and cosecant is written as 1 over sine. So we now have this fraction divided by that fraction, which is, you know, the signs are going to cancel out, and we have cosine over 1. And so we're left with cosine. So this whole thing simplifies down to cosine. Isn't that nice? Okay, let's try another one that's a little bit more complicated. What about this expression that you would need to simplify? So we have sine to the 4th minus cosine to the 4th plus 1 all divided by 2. So something to think about when you're doing these is all the things that we learned in algebra are kind of fair game here. So factoring is a skill that you might end up using. So if you look at the sine to the 4th minus cosine to the 4th, maybe that triggers something and you remember that that is the difference of squares. So I could actually write that as sine squared plus cosine squared multiplied to sine squared minus cosine squared. And then of course the plus 1 over 2. After you've done that, remember your Pythagorean identity, sine squared plus cosine squared, that's equal to 1. So we can replace that with 1, which really doesn't need to be there, right? So we have sine squared minus cosine squared plus 1 all over 2. Now what we're going to do is we're going to rewrite, and I'm just doing this so that you can see it a little better, but I'm going to reorder these and put it as 1 minus cosine squared over 2. Because what I can do now is, if you remember your Pythagorean identity, that sine squared plus cosine squared is equal to 1. Well, if I solved that equation for sine squared by subtracting cosine squared from both sides, I get 1 minus cosine squared. So this whole expression of 1 minus cosine squared can be replaced with sine squared. So sine squared plus sine squared divided by 2. Well, now you have 2 sine squareds divided by 2, and then the 2's cancel, and you're just left with sine squared. So this big old mess right here simplified all the way down to sine squared. All right, that's one type of simplification that you can do. Another type of simplification is where they actually tell you specifically which trig function they want you to rewrite your expression in, which means your expression can be as complicated as it wants to be. The only stipulation is that it can only use this trig function. So in this case, we can only write it with cosine. Cosine squared cosine times cosine plus 1, whatever, but only with cosine. So let's try this. 1 minus sine squared multiplied to 1 plus secant squared. Well, first of all, we can do that same trick that we did before, that if you take your Pythagorean identity that sine squared plus cosine squared is equal to 1, solve for cosine squared, and you get cosine squared is equal to 1 minus sine squared. So I can replace this with cosine squared. And then remember that secant is the reciprocal of cosine, so this is really 1 plus 1 over cosine squared theta. Now technically we've achieved what they asked us to. We wrote this in terms of cosine, but there is a really quick little simplification that we can do, and that is to distribute my cosine squared. So if I did that, I end up getting cosine squared plus 1, which I think is a little bit neater to write. Okay, let's try another one. What if I gave you cotangent, and it's just cotangent, and I want you to write that so it only has cosine? This one's really hard. Okay, well, first of all, we know that the cotangent of theta is equal to cosine over sine. So we got the numerator, but what are you going to do with the denominator? Well, remember that sine squared plus cosine squared is equal to 1. And if I subtract cosine from both sides, I get this 1 minus cosine squared. We've been doing that in a couple problems already. But if I take the square root of both sides of this equation, I now get sine is equal to plus or minus the square root of 1 minus cosine squared. So I can now replace this with that, and then I have my answer. I'm done. And technically, if you really wanted to, you could rationalize the denominator, but we're not gonna. We're just gonna be done at this point. Okay? So lots of things that we can do with our identities. So far, we have proved an identity, we have simplified identities, and we have rewritten expressions in terms of specific trig functions. Okay? So maybe this is going to be a little bit better than the graphing for you guys. Maybe not. We'll see. That's it for now, folks. Talk to you later.